This week, we are starting to think about the way that the sky is divided up, and more importantly, we're going to talk about time and how change. We're still hanging around Earth this week. We're going to move away from Earth soon. But we're starting to think about how people have come to understand change, and of course, this concept of time plays heavily into that. We're not going to really have much of a chance to think about the ancients anymore, at least for a couple of weeks until we start thinking about the naming of the planets and so forth. It does occur to me that there's some preface necessary before we dive into some of these terminologies, because I feel like it could be very easy to think that I'm nitpicking with a lot of these terminologies, right? Why do I spend so much time on the definitions of these words, right? Time is a really, really important word in astronomy. Actually, it's a really important word in general, in science especially. And I think it's one of the most misunderstood concepts in the universe, essentially, in the world. And I think it matters. I think it's really important. This is one of my favorite books of all time. It's actually a journal that was kept by this Roman emperor back about 2,000 odd years ago, and it's really interesting because this was arguably the most powerful person in the world at the time. The Roman Empire was at its height. And he never intended to publish this. It was actually dug up, much later. And in his personal journal, it's this absolute abject obsession with finding his role in that position and what he owes to the universe, essentially. But more importantly, I think that he is concerned with learning how to think, and he's deeply obsessed with the concept of philosophy at the time, which, philosophy as a discipline was inseparable from education at the time, right? The idea that you needed to learn how to think was paramount to education. I think that there was no way of separating that from the university experience. And so, this being a general science class, I think that a huge goal of this course is to get you guys to think about some of these basic ideas that you've heard a million times in high school and rethink them a little bit, and rethink not only what they mean, but why we should even care about what they mean. I'll read you just one sentence out of this book that I came across this morning that I think is really, really critical. And this is going to be kind of the anchor point from which we're going to build the rest of our discussion. So this is Marcus Aurelius, the Roman emperor. He writes to himself, "If it be not fitting, do not do it. If it be not true, speak it not. Ever maintain thine own purpose and resolution, free from all compulsion and necessity." So what's he saying? He's saying, if you're going to do something, if you're going to say something, make sure that you mean it. And it's very dangerous that you could pass through an education pipeline and come out with all of these facts that you learned in a book somewhere and not have any grounding in defense of why those facts are assumed to be facts in the first place. So if we accomplish anything, I want you guys to make sure that each of these ideas that we're going to present, that you understand why people believe they are the way that they are. Because science being a progressive discipline means that they're going to be different 1,000 years from now, for sure. They might be different in minuscule ways, but they might be different radically. And the only way that we're going to make that progress is by rethinking the underlying assumptions at each point. So when we think about this huge concept of time later today, I want you to bear that in mind, that there's a lot of confusion about that word, and it leads to no end of headaches and all sorts of mystical interpretations in science even at this point. And we'll talk about some of those at some point. But one of the first things that you realized probably when we were going through our first week and talking about some of these basic definitions was that time and distance are inseparable in modern physics, right? We only have light in order to gauge what's happening beyond our immediate surroundings here on Earth. And from that, we assume the speed of light to be constant in a vacuum, which it certainly appears to be. And so we assume we can gauge distance by time, by the travel path, right, how long that takes. Now, we'll get back to time in a minute, but let's bear that in mind because we need to wrap up a couple of super important ideas from last time that I didn't quite have a chance to expound upon, and I think they're really important. And the most critical of those is this word mass, from which all of these other concepts like inertia and conservation of energy and things like that fall out of, which are going to keep coming back to punch us in the face if we don't make sense of them. Now, I told Dusty, right? It's Dusty, right? I told Dusty that I would touch on this problem a little bit with more detail about why it is that we think the planets are all in a plane, essentially. I thought a bit about this, and I think the best way to explain this really comes down to one of Newton's recognitions. Right? Newton had a few of these basic laws which seem a little bit pedantic at this point, and one of them was that something that's moving tends to stay moving unless something gets in its way, right? Unless you stop it. This makes sense. We all recognize this to be true, but it turns out to be critical. So the basic idea is that when these solar systems are forming, that there is a process by which the aggregation of material increases the gravitational pressure. And we'll talk in a second about what gravity really means. But let's say that it means that the more atoms that are around, the more they're going to pull on the things that are near them, right? Each atom has some ability to pull on its neighbors. Well, as those atoms are tightening up and pulling, and there's an aggregation at the center of these newly formed solar systems, which eventually becomes a star and everything else, what happens is it begins to spin. Now, you can see this if you guys ever watch the Olympics and see these figure skaters, right? And they do this, actually skateboarders too, like Rodney Mullins is actually incredible at this, right? They'll do this thing where they'll be, moving normally, and all of a sudden they'll take their arms and pull them in tight, right? And as they do that, they begin to spin faster and faster, right? And this is a basic law that falls out from these inertial relationships, which says that momentum in that body has to be maintained. So as you bring it closer, you have to actually increase the speed to make up for the fact that it's not spread out over such a distance, right? So the figure skater starts going faster and faster. The star system starts spinning faster and faster. Now, as it does that, we have to pay attention to this other concept, which is that those particles, right, those atoms, want to stay in motion. They want to continue the path that they're going. And so all of this business that we talked about last week, which is about orbitals and gravitation and so forth, it concerns this balance between this, you're swinging around the sun, and in some sense the Earth wants to fly away, right? It's moving forward. It's moving forward, right, as it goes around the sun. But the gravity, which we'll talk about in a second, there's a balancing, for lack of a better word, let's use Newton's word, force. There's this balancing pressure that holds it to the sun. And so there's this very tight, delicate balance between those two. So what happens is that around that spinning axis, there is a tendency for things to spread out along that spinning axis. And that's essentially why those things end up in that plane, because the plane is centered on the axis of the spin. I hope that helps a little bit. So let's unpack that idea of gravity a little bit, because this is actually one of the most outstanding questions in all of physics as far as I'm concerned. Maybe light being the second one, which is perhaps the other side of that coin. When we talk about mass, and we briefly touched on this at the end, but I'll just repeat myself because I think it's very important. The word mass comes from Newton's ability to scale Kepler's laws of motion of these planetary bodies, and then he adopted it he really integrated the concept of weight on Earth to match that concept, right? So weight is what is experienced by something that possesses this mass, this gravitational attraction, which is essentially atoms. Now, this is important because there's this huge crisis in cosmology and quantum physics and really just fundamental physics in general, which is that there doesn't seem to be a way to unite the concept of gravitation at a big scale with the very tiny, the things that happen at the atom and at the scale below the atom. And so there's a huge endeavor, which is essentially considered the search for quantum gravity. Now, perhaps this is such a problem because the concept of mass was never really meant to be applied to something other than atoms themselves. And so if we really take Newton at his word for what this word mass means, it seems like it is something that atoms do to one another. And perhaps the problem with finding something that atoms do within themselves and trying to make that about mass is not an appropriate way to look at things. And actually, if you think about where this first started, at some point, I know the point actually, at some point, people were studying electricity, and they came up with the idea of this electrical fluid, which ended up becoming the electron. But why did it become the electron? Well, they had these things. I don't know if you guys are probably too young to remember these, but they used to, our old computers and our old television sets were these big hulking things, right? And they had these huge tube systems inside of them. It was a vacuum, actually, the size of the TV screen. And the idea was that you were directing this beam of electrons to the back. You control it with magnets, essentially, and you can point this beam of electrons. And so people discovered these beams. They called them cathode rays. Well, they initially thought, okay, maybe this is something like a beam of light, right? But what they realized is that it could be deflected magnetically, and this isn't something you can do with light. And so they thought, okay, the amount of deflection, the amount of magnetic force we have to put into this thing tells us that it has mass, right? That it has some inertia to it, right? It wants to stay its course, which is, in some sense, very logical deduction. But there may be problems with that, too. And so at some point, we ended up with the idea that things smaller than the atom could possess this ability to stay the course, so they should have mass as well. And it's not entirely clear that that's the case. There's other ways to interpret this experiment that might be more accurate. For instance, those aren't actually vacuums, right? There's no way to actually make a vacuum. Did you know that? You can't actually get all of the atoms out of any space. It's virtually impossible. Now you can get a lot of them out, but there's still some atoms in there, right? And so it's not clear that those atoms aren't doing the job of conducting that path from the front to the back, and that those atoms themselves can't be displaced in some way that has some inertial qualities to it. So again, we have to really think about what these words mean because they affect our downstream assumptions, and they can maybe lead us out of the brambles, right? Because if any of you go into fundamental physics, you will run up against this problem, right? Gravity is a nightmare, especially when it comes down to unifying it with what atoms are actually doing. So we have this beautiful mathematical theory right now. It's been standing. We essentially have this demigod, this almost deified individual named Albert Einstein, who you've probably heard of since kindergarten. Because Einstein essentially made an improved mathematical rendition of Newton's gravitational laws. And I don't have time to break down for you exactly how he did that, but we'll do it next semester if you stick around. So it's extremely accurate. It's a very predictive mathematical relationship. But the problem is it doesn't tell us anything about what those atoms are doing to one another, right? So it's actually I don't know if any of you have had this sort of childlike moment when you've been walking down the street and thought, man, it's pretty strange how I'm stuck to the ground right now, right? There's nothing I can see between me and the ground, but I can feel it pulling on me, which is very, very strange. And magnets, too, have this same kind of magical ability to them. But there's something that those atoms are doing to one another, you can rest assured. There is some mechanism available by which they're able to do that. And so that mystery is just at the absolute spear front of our understanding right now. And I think that unpacking that mystery is going to come down to understanding this word right here. All right, before we go on to today's lecture, I want to make sure that we have covered all of these things. Density, if you guys come across this word before, this is really just how much stuff there is in some given volume, right? Basically in a box, how much do you pack stuff in? Let's see what else we got here. Okay, so there it is. So Newton essentially took Kepler's law, which was a proportionality, scaled it by this concept of mass, right? The bodies have slightly different orbits because orbital speeds, let's say, their periods, the time it takes for them to orbit is slightly longer or shorter because of how much stuff is there, which is a really profound recognition, actually. And I've kind of beat you over the head with this already, you know, this balance idea, right? That everything is in this beautiful balance of push and pull. Everything wants to fly off the leash, and everything is, in some sense, stuck to the sun. So this is the equation. This is the absolute master equation that Newton is probably most well remembered for. I don't know that he would be such a titan of math and science without this relationship. So this is actually quite interesting too, because Newton famously has also introduced this constant of proportionality, which is this G factor, and it's a really ugly number. You don't need to know what it is, but it has this very, very perplexing units to it, which I don't actually have on hand right now. But what this says to us is actually, I'm going to draw you a picture of what this law actually means. What this law means is that the gravitational force falls off in this radiating law, right? And light does this too. For every unit distance that you move away from a source of light, its intensity is going to fall off by a square of that distance, right? Now, that's a really boring mathematical idea if you're not a mathematician, but it's very easy to understand for light because you can think about light as having little rays, right? There's rays of light. This is an old idea. It does appear to be ray light. Actually, I know a few of you are digital media majors. Does anybody do 3D animation or anything like that? Not yet? Well, you will. You should. It's fun. There's a free software called Blender. You should download it and play with it. It's really cool. Anyways, Blender and a lot of these 3D rendering, you know, the Pixar studios and all of this, the way that they actually do these beautiful 3D graphics is they calculate the ray tracing, right? So they'll calculate how these rays reflect off different surfaces, and they can give them different granularity. And you get this reflection and scattering, and essentially it looks real because of that. So they do this ray tracing. Well, anyways, if you imagine the rays of light coming from a point source, it's easy to see how at 1 unit distance, say r up here, you have 4 rays going through any square area, right? But as you get, say, twice as far away, now you only have 1/4 of those rays that are going through that 4 times, through that same area, right? There's only 1/4 of those rays. And gravity does the same thing, which is really fascinating, and I think that a really good analogy, if not even mechanistically important, is that gravity is also ray-like in this way. And if you can, you know, this Persian, I believe it was a Persian scholar, in his writings actually treated gravity as rays, which is really interesting. He sort of said, what if these atoms are connected by cords of some sort, like cords of light? Well, if they are, then you can actually think about gravity in a much more interesting way, because it's almost like these atoms are leashed to one another, and that there's some radial architecture to those atoms such that all of these leashes fall off with this same relationship. I'm not saying it is so. I'm saying this is actually a really productive way to think about gravity. It's actually, I think, a much more useful way than trying to warp these ideas like space or something like that, which gets into strange abstract territory very quickly. So, gravity. It is a pull between atoms, and it appears to be ray-like in this same inverse square relationship. And Newton noted this. Now, it actually wasn't Newton that came up with this inverse square relationship, sadly. And this is kind of an interesting aside that's maybe worth taking your time for. Newton found out about this inverse relationship in a correspondence privately with a gentleman named Robert Hooke. Hooke is famous for his study on elastic mechanics. And Hooke was very bitter that Newton actually went forth and garnered all of this fame as a result of this inverse square relationship. Now, that's not to say that Newton didn't improve upon the idea. He found the way, like I said, to scale it with this concept of mass. He realized that the mass was also important. How many atoms were there was important as well. But the idea actually stems back to Robert Hooke. And I think Hooke died very bitter as a result of not being credited with this, which is quite interesting. Credit is a very interesting thing in science. You know, you might think you probably learned in high school that you should credit all of your sources, right? And that's all well and good, and you should. But there's something very interesting that happens when you move into the higher echelons of publishing, right? So I published a paper this last summer in the journal Nature, which is I would say it is probably the most premier journal in the world. They give you 30 references for your paper, 30. And you might think, well, 30 is a lot of references. It's not, actually, right? I must have read 1,000 papers to concoct the ideas that went into that paper with my colleagues, right? I didn't publish the paper alone. And so how do you whittle that down to citations that are relevant? Well, you pick the people that have done the most work in those fields that other people are going to be able to relate to. So the referencing is in some sense done in order to integrate your ideas into the landscape that's already present, because your job as a scientist is to make your ideas useful to the people who would most use them, which are generally your peers. And so this citation business is a bit more complex than, hey, you should cite the people whose ideas you're leaning upon, because that's technically impossible. What you have to do is actually cite the people whose work is ongoing in that discipline in order to relate it to it. And I think that's what Newton did. And the tragedy is that Robert Hooke didn't get a shout out. So, you know, it's a complex business, citation. All right. I don't really want to go into this too much. You know, Newton contemplated a little bit about this idea of what it would take for a planet to rip off of its leash and fly off into the distance. And he contemplated it more in the idea of how would you actually throw something into space? Could you get something into orbit? And so, you know, mathematically, he understood that you could. And one thing that's maybe worth contemplating as we go forward is that the velocity that you need, how much speed something needs to be able to escape its orbit, has nothing to do with the size of that body itself. That's really, really interesting, actually. So it entirely depends on the mass, the gravitational attraction of the larger body, in our case, the Earth. So when people are trying to calculate how fast they need to shoot those rockets to get them into orbit, it doesn't matter, actually, the weight of the rocket itself. And actually, this is escaping the orbit itself, right? So how do you get something, say, to the moon or out to Mars? How do you escape our own orbital path? It depends exclusively on the mass of the Earth in that case. That's really fascinating. All right, so this is quite productive. So what you can see here, we use this escape velocity concept in order to hop around through the solar system. Yeah, question?
I was wondering if it's true that if like everyone jumped on the Earth, would the Earth like change its orbit? Is that possible?
If they jumped on one side of the Earth, perhaps, yeah. Actually, this is a real concern in some sense. Not that people are going to jump up and down at the same time, but that when we actually do this slingshot maneuver, so if you see here, this is, I'm not sure which spacecraft this is. Did I write it down? No, I didn't. Okay, well, oh, it's Voyager 1. Okay, great. This was a probe launched back in the 70s, I believe. There's a real concern that amongst some of the engineers studying this, that what happens is when you go to each one of these planets and you zip around it and then launch off in the other direction, that you slow down that orbit by a tiny bit. And that if we keep doing that for hundreds and hundreds, maybe thousands of years, that we will appreciably mess up the orbits of these bodies. Now, you know, I think that turned out to be unfounded because the change is so minuscule, right? But as we build bigger and bigger complexes, this is going to be something we will have to consider, I think, to some extent. So, yeah, actually, and another interesting thing, the way this can play out maybe more appreciably is Have you ever seen these pictures of guys on the space station jogging on these little, or on these exercise bikes or something? This is really dangerous, actually, it turns out. So when they first started doing this, they noticed that they would shake the thing out of its orbital path very quickly by doing this. And this is kind of a smaller version of your question, which is, could we do this to the Earth? And so what did they do? Well, they had to actually mount these exercise machines on these very intricate spring cushions, essentially, so that the impulse was taken up by the springs as opposed to being transferred to the body of the spacecraft, the space station, right? So yes, it matters. It matters a lot, and it's unclear how much it's going to matter in terms of the actual planetary dynamics. But I can tell you this. The planetary orbits are absolutely very delicately balanced. There's, and this is something that's a very unpopular opinion, but there is a really, really interesting, if you guys want to check it out, there's this magazine called Quanta magazine, which might bore you to tears for the most part, but there was a really interesting article by these three, that concerned these three mathematicians who were examining this question of how stable our solar system was. And the conclusion that they all kind of came down upon was not very, actually. There's a very delicate balance between the forces. We are flying, according to this heliocentric model, which we all subscribe to at this point, we are moving really fast in this orbit around the sun. We're covering hundreds of thousands of kilometers every day, right? This is, well, that's not true, every year. So between the seasons, the arms, right, hundreds of thousands of kilometers. So we're moving very, very fast. That's a lot of momentum in the forward direction. And there's a lot of attraction from the sun. The sun has a tremendous amount of atoms that are all pulling on us, right? But that balance is still razor thin. And it's stabilized by the orbits of all of the other planets and so forth. So not only do we depend on our own mass and the sun's mass to remain constant, which they don't. We're losing tons of material every year, and the sun's losing tons of material every day, probably. But we're also dependent on the orbits of all of the other planets around us because they, in some sense, stabilize our own orbit. And so this is not to say that everything is going to fly apart, but it is interesting when you move, especially next semester when we consider why our solar system looks the way it does. Well, it hasn't always looked this way. I think it would be extraordinarily naive to think that it does, especially since our solar system is full of all sorts of weird planets, and most solar systems aren't. They have one kind of planet, right? And so it seems like there's been a lot of change in our solar system, and nobody really has the means to deconvolve that. But it's certainly an interesting thing to contemplate. All right. And there's this other aspect, too. It's very easy to use this. You might have noticed in the Newtonian gravitational relationship, there's two bodies, right? Because two bodies are actually quite easy to calculate the gravitational relationship between. The problem is you throw a third body in there, and things actually balloon into extraordinary complexity, right? It's actually, you need a set of 9 second-order differential equations to model three-body interactions. And that means that there's actually no real general solution that can be expressed in terms of a finite number for that gravitational attraction at any given point. You can't actually even do it. And this is, every once in a while you'll see a headline of some whiz kid has solved the three-body problem in some context, but it's always in some very confined context, right? And it's even, people will argue about whether they've even done this. Okay, so that's 3 bodies, right? What about 4? What about 10, right? It just becomes extraordinarily, I would say, impossibly complex to deconvolve and make predictions really about the long-term relationships of a lot of these bodies. And I'm not saying this to scare you, to make you think the solar system is going to fall apart anytime soon. Obviously, these systems have survived. There's a selection process that's gone by. Let's say there was 20 planets in the solar system originally. Well, the ones that weren't stable didn't make it, right? And the ones that did are here. And so there's something about that selection process which has granted us the ability for life to develop on this planet. It hasn't been a very fast affair, right? By all reasonable estimates, it's taken several billion years for us to get to this point where we're sitting in a lecture hall and not, squirming around as single cells in the ocean. So there's a great deal of stability, but there's also a great deal of instability, and that probably is important in terms of the ability to even get where we're at. So, all right. And then the last thing you might have come across in your textbook is this really cool story. And again, this is another triumph of engineering and mathematics, is that at some point, I think this is in the early, let's say, mid-1800s, people were studying the motions and particularly trying to reconcile the motion of these bodies. They'd taken very good charts. Tycho made incredible charts, but people had been continuing to make great observations of the sky. Newton proposed this new relationship that governed the motion of these bodies in the sky. And people started to try to reconcile them with the observations. And they didn't quite work out in some situations. And some theorists at the time began to ask the question of, well, in particular, Uranus doesn't seem to be moving the way we should expect that it's moving. It seems like something else is going on with Uranus. What could be going on? And someone said, well, if there was another planet out there and it was tugging on it like this, maybe that would explain why Uranus's motions don't correspond to this Newtonian relationship that we've adopted. And so they put out a call to all of the astronomers and they said, hey, if anybody can find something tugging on Uranus, we'll give you a pat on the back. We'll give you a prize or something, right? And it only took them a couple of years for these two gentlemen, John Couch Adams and Urbain Le Verrier, who discovered this almost simultaneously. They discovered Neptune, right? They pointed their telescopes at the place where they expected it would be in order to produce these gravitational effects, and they found it. They actually found it sitting right there. At the time, Neptune's, it's very dark. It's hard to see Neptune, actually, even with a telescope in your backyard. It's considered a dark planet, which is sort of ironic because it gives off twice as much light as it receives from the sun. But it's still very, very dim and difficult to see. So, yeah, those dark things, right? Those dark things have explanations out there. I think that's really important as you see these pop-sci headlines about dark this and dark that and black this and black that. And there's something happening, right? It's very easy to imagine a different universe where instead of proposing that there was a planet there, somebody just said, well, there's just some dark matter gunk out there that's messing up the orbits of these things. And they just moved on, and they put a placeholder in their equations for it. And we never discovered Neptune, maybe until we actually built some huge telescopes like today and just came across it, right? Okay, so let me recap everything from last week really quickly. We talked about the celestial sphere. Celestial sphere is essentially the way we divide up the sky. It's a very ancient conception, right? It's observer-centric. It's very relativistic in that sense, in that we're talking about how things move with respect to us, which turns out to be very practical. We talked about orbits, which are these elliptical balance of gravity and forward momentum. And then today we've just gotten into gravitation, which is really important. So I'm going to change gears now, and I want to talk to you about time, essentially. And the way we're going to do that is we're going to talk a little bit about seasons. We're going to talk about timekeeping. We're going to talk about the motion of the Earth and how that's been useful. And then we're going to get into, we'll hopefully make a real interesting dive into how the changing seasons and so forth have affected us on Earth in the long run, because we need to talk about climate a little bit. And actually just the fact that I just said the word climate is going to lead to a little warning at the bottom of this YouTube video, which is going to say, that climate change is this anthropogenic business and so forth. So climate is a really hot topic. That's my point, right? Not that climate isn't an important topic, but it's obviously one of the central pillars of discussion in the geopolitical sphere right now. So it's a really, really important topic, and I want to give it its due, time, because we need to unpack the concept of climate a little bit. It's often mistaken for weather, which it's not. It's often mistaken for seasonal effects. Whatever your weather is tomorrow, and you'll see this in the news all of the time, that people will say it's the hottest day on record or something like that because of climate change, right? Which is preposterous, because climate has nothing to do with what happens day to day, right? It has everything to do with these large-scale changes in the patterns of weather on the Earth, and the temperature, and the glaciations, right? And we're going to get into that. And so I hope I can make it into that today, but if not, we'll deal with it next time. But first, let's talk a little bit about how we divide up the Earth. We talked a bit about latitude last time, right? And how you could measure the latitude. Did anybody actually play with that, with the fingers and the pole star? Has anybody been able to see the pole star? Do you look? It's a hard one to see. Actually, where I live, the pole star is kind of, I live up by Grants Pass, but not really. But the pole star is over Grants Pass, and so all of the light pollution makes it almost impossible to see the pole star. But yeah, I don't know. Keep an eye out for it. See if you can figure out your latitude using the finger trick that we talked about. At any rate, this is essentially how we divide up the Earth, is with this concept of latitude. That gives us our kind of north-south divisions, right? Which, of course, really just has to do with how high the pole, the axis of the pole is above the horizon for you. Now, longitude's a bit trickier, right? I think it's always, I may have mentioned this earlier, but it's always been a bit trickier because you don't have any easy way to pick out how far you are in this east-west fashion, right? You can't just look at the sky and figure it out, which is kind of a nightmare for all of the early navigators. What you need in order to figure out your east-west position is some sense of how far you've gone. And to figure out how far you've gone, you need to know how fast you're going, and you need to know how long you've been going for, right? And so that's come down to increasingly good systems of keeping track of time and speed, right? You may have heard of the nautical speed, which is called knots, right? And the way that they did knots originally, and actually for very close up until the last couple hundred years, really until they had better sensors in the 20th century, was they would literally throw a rope out the back with knots tied in it and see how many knots are pulled out of the bucket. And that gives you a sense of how fast you're going. And the timekeeping systems were equally crude, right? We're talking about hourglasses and sundials and things that are very tricky. And we'll talk about the problem with all of those in a second, especially when it comes to relating to what time actually is. So all of these latitudes, right? All of these longitudes essentially are what we call great circles. And what's a great circle? Well, it's essentially just the biggest circle that you can draw around a sphere. And these great circles go through the poles, right? They give us a measure of how far we've gone east to west. Now, there's something kind of funny that happened. It's easy to set up latitude where you essentially say that your 0 point is the equator, fair enough. And you essentially go up. You're measuring, of course, that angle to the pole. And when you're at the North Pole, the angle to the pole is 90 degrees because it's right above you. The pole star is right above your head. Okay? It's a little bit trickier with longitude because, excuse me, where do you draw a 0 point for longitude, right? You have to pick some arbitrary place, actually. And, some of you may be aware of this already, but the place that they picked was this spot in England, this town, Greenwich, actually. Now, at the time that this was happening, England was the great naval superpower on Earth. And this had changed hands quite a bit during the colonial era. Spain had a hand in the game for a while. Portugal was a big player. Who else? France, right? But by the 1800s, England was the dominant superpower on the seas. And so they basically got to set up the rules for navigation, sort of like how the United States sets up the air traffic rules now. I mean, I don't know if you guys are aware of it, but all of the pilots all around the world have to speak English when they're talking to the air controllers, right? So this is in some sense important because you need to be able to standardize these things, right? Otherwise, how do you call for help if you're in the wrong country all of a sudden and your plane breaks, right? You need to have a standardized language. And in this sense, the British standardized that 0 point of longitude to their own state, their own home, which was in Greenwich. And so by the late 1800s, most of the countries that were navigating the seas were using this. And it just became the standard. I think about 25 countries, some of the superpowers in the world had ratified that by about 1884 or so. But anyways, Greenwich, why Greenwich? Well, the Royal Observatory was there, okay? So that made a lot of sense in terms of charting the skies and so forth. All right. Now, we have to get into something a little more abstract, and I'm going to not spend a ton of time on this because I don't think that it's really important for your understanding the rest of our topics in this course, but you might want to be aware of it in general, because if you ever get into astronomy, this is how astronomers will tell you how to locate a star in the sky. So, if you're like, where do I find Saturn tonight? Well, probably the best way to do that is to get an app on your phone, right? Those are pretty cool apps, like, I forget what they're called. There's a bunch of different ones, but the little star finders, and they use the GPS on your phone, and you can just find the star. But anyways, before that, people would probably tell you where things are, and the way they would do that is by this system of declination and right ascension. And so there's this system concocted, which is used for most of the star charts today, which is about right ascension and declination. Now, it's a little bit tricky to understand. So declination is a little bit easier. So it's very similar to the celestial equator, right? You're just measuring the ascension of something, the motion of it, the location of some body with respect to the celestial equator. Right ascension is a little more arbitrary. The right ascension 0 point is set where the equator of the Earth intersects the path of the ecliptic, which is the motion path of the Earth around the plane in which all of the planets sit in our solar system. It's where the equator hits that path on the spring equinox. Very arbitrary, but you can see that it happens to be sort of right there in this picture with respect to the celestial sphere. And then, so right ascension is really just the amount that you shift to the right, looking from above, from that point, right? All right, I won't bore you with this because it's not really necessary. Although you might have a quiz question or something about how to calculate that, so be aware. And your textbook will go into more detail about that. Right ascension, unlike declination, is not measured in degrees, which is also equally perplexing. This is a very cumbersome system in my opinion. So we measure right ascension in terms of hours, minutes, and seconds. All of these things are really divisions of 60 again, which is something that we all take for granted. But remember, where does that come from? It comes from the Sumerians, right? They didn't use base 10, they used base 6, which is very strange that we still use it. This is how our clocks are set up, right? This is how we divide the circle into these units of 6 as well. It's very, very strange that we keep doing this, but we do. And so right ascension carries on that tradition. Here's a little animation of how that's set up again for you. Again, it's where the celestial equator intersects the horizon at a right angle at the spring equinox. And you can see a little picture here. Earth's orbital sphere, the equator, and you get that intersection point on the spring equinox. Now we're going to talk about what those equinoxes are today as well. I'm not going to bore you with this. All right. Now, what dividing the sky up into is that we end up with this very standardized chart. And if you open an astronomy sky chart, you'll see this grid, which is essentially the sky divided up in this fashion, which has to do which covers the entire 360 degrees of the sky during the night's rotation around, right? You get the whole view of it, and it's laid out in this fashion, which is divided up in terms of right ascension and declination. So this could prove useful if you ever want to crack open a star chart and see where things are at any given moment. Okay. Now, before we can talk about time, we need to talk a little bit about the turning Earth, right? Because I think that, from the Greek onward, right, we established that the Greeks had essentially convinced the Western world that we were on some sort of rock that was let's say for all intents and purposes floating in space, and that the sun was also something like a rock that was very hot. And the question persisted about this turning of the Earth. Was the Earth actually turning? And actually, this question persisted all the way up into the 1800s. The way that they solved this problem is actually quite fascinating. This this gentleman named Foucault actually came up with the solution. And he did it in a very peculiar way. People were coming up with these solutions about timekeeping, you know. And one way to keep time is that you look for some periodic predictable motion, right? So an easy way to do that is obviously an hourglass or something. But another way to do it is with a pendulum. You know, you guys have grandfather clocks in your house? Your parents have these things? A couple of them, right? And the way that they work is that you essentially have this weight, right, which is dangling, and it's going back and forth. And it does this in a predictable fashion. Actually, the period, the amount of time that it takes for that to complete a swing is very predictable, and it depends upon the mass and so forth of that pendulum. So what this gentleman realized is that, okay, in a stationary system, a pendulum is going to be just swinging back and forth. But if that system is in any way precessing, that is rotating, that the pendulum is also going to start rotating like this. And so he said, if I can build a big enough pendulum, I think that I could actually calculate the rotational effects, let's say the speed of the rotation of the Earth, which of course we understand should be about a day, right? And he did this experiment. He built a huge pendulum. He did it in the Pantheon in Paris, and I believe it's still there. Yeah, so that's what this picture is. And if you've been, yeah.
I worked in Columbus, Ohio, surveying. We staked one of those out.
Oh yeah?
For COSI.
COSI, that's right. I volunteered there when I was a little kid.
Yeah, we
Yeah.
actually all the points for their pendulum.
Cool.
Timekeeping.
That's really cool. Yeah, so a lot of science museums have these things. I think, I think the Exploratorium might have one in San Francisco too. Pretty cool stuff, right? So they basically start this thing swinging in the morning, and it traces out this path as it moves each day. And it's due to this rotational effect, like I just showed you with my car keys, right? I can predict this rotational effect if I know the mass and so forth. And I won't bore you with the math of that. But it's pretty cool. So this guy, in some sense proved the obvious, but he did it in a quantitative way. And so it was very convincing, and people didn't really debate whether that was the case. This is a schematic. You can find it in your textbook as well. Which brings us back to this grandfather clock and this idea of keeping time. So I want to pause for a second and think about this question of time. Can anybody tell me what time is, actually? Yeah. What was that?
A social construct?
A social construct. Can you elaborate on that for me?
Well, we invented time to make the world make sense.
We did. We invented time to make the world make sense. Yeah, so time is certainly an invention. That's absolutely true. I mean, there's no doubt that things change, right? This is a physical fact of reality that there is change, right? I just changed positions in the physical universe. Everything that we do involves change, particularly in physics in the material world. Things are changing constantly. In fact, things seem to be falling apart and coming together almost constantly. So in order to keep track of that change, we need some system of doing so, right? Any other ideas? Yes?
Dimension.
A dimension. What's a dimension?
So like you have the spatial dimensions, right? And then you have time dimensions.
Right, so in that sense, I think what you mean by spatial dimensions is ways of measuring some aspect of the material world, right? Essentially giving you, when you think about spatial dimensions, which are, the concept of dimension is actually an architectural term, and it was originally reserved for length, width, and height, right? These are essentially the measurements which could allow you to get grips on some material body, right? And so this idea, actually, this is the Einsteinian conception that time is also a dimension in some sense, that it does in fact qualify the measurement of change, right? So it is a physical measurement of a physical system in that same sense. Anybody else? All right. Well, I think you guys are both onto something very important. So time is what we use. It's a measurement of how we quantify the rate of change of a system, right? Now, if you want to quantify the rate of change in any case, let's back that up. If you want to measure something, how do you do it? Let's say I want to measure the length of this Marcus Aurelius book. How do I do it? I need a ruler or something, right? And what is a ruler? Well, it's a standard, right? It's a standard of measurement, right? It's completely arbitrary, but it's really important, actually. Let's say I want to measure how heavy my coffee cup is. How do I do that? I need a scale, and what is the scale? Originally, what is the most primitive scale you can imagine? It's a balance, exactly, that's right. So what I would do, what do I balance it against? A standard of some sort, right? And it's actually pretty funny. I don't know if they still have it, but when I was in college, they did. I haven't looked into this in a while. But for a while, there was actually a kilogram. There was literally the master kilogram that they kept in this vault somewhere in England, right? And every time they would take out the master kilogram to calibrate some system, let's say to make a copy and make a balance, right, and make new versions of the kilogram as a standard, they would actually have a guy who carried the master kilogram, and there was another guy who walked behind him to catch him if he dropped it, right? It was that much of a standard. It was so important. Now, of course, there's other ways. We have much more sophisticated ways of calculating mass, and of course, you can do it with water to some extent, but that depends on your height, right? Because as you see, remember we talked about weight is different from mass, right? Weight tells you the gravitational effects of some mass. So that block, that master kilogram, is the unit of mass. That's how many atoms of a particular variety of atoms are there, right? But the weight depends on the height. So if I go down, let's say, down to sea level, my master kilogram is going to weigh different than if I go to the top of Everest. That's very perplexing, but remember, the distance matters, right? Your gravitation falls off with an inverse square law. So your weight, the feeling of gravity is going to change. And this gets into some really, really interesting territory, okay? But I'll get to that in a second. So you need a standard of measurement, right? And so clocks do that, right? Clocks form a standard by which to measure the rate of change of physical systems. Now, you might think that time had a better definition than clocks. But in physics, when we say time, what we mean is what our measuring standard is doing. When in all of the Einstein equations, in all of our deep discussions of time, fundamentally, if you really go back and read the texts, what you'll find is what Einstein meant by time was what clocks do, okay? This is very different than the mystical interpretations that you might hear in the popular science media about time, right? And there's a lot of paradoxes that result when you get confused about this. You know, one of them, let's explore this a little bit more. So I have a standard, let's say my pendulum clock. We started with that. Now, if I take my pendulum clock and I use it to see like how long it takes for my toenails to grow an inch or something, whatever, some arbitrary thing, right? Well, it's going to give me some readout, right? And it's predictable. And so every time, this standard process unfolds, it's going to be that way. Well, what happens if I take my pendulum clock to the top of Mount Everest? What's it going to tell me? It's going to say that it takes longer. Yeah, really. Because the pendulum depends upon the weight of that pendulum, actually. And the pendulum is going to go slower when there's less gravity, as there is at the top of Mount Everest. What happens if I take my pendulum clock into space? It's going to tell me that my toenails took forever to grow, actually. Now, this might seem like I'm just splitting hairs here, but this is not insignificant, actually. So, one of the proposals by the popular science media is this, and actually by a number of very famous physicists, and I'm surprised that they make this error, is that they have these very sophisticated clocks today. They call them atomic clocks. Okay, well, what's an atomic clock? Well, it's not that much different than a pendulum, right? It's essentially an atom. Well, it's a crystal lattice of atoms that have this pulsation to them, right? So all atoms pulsate, and we don't have to get into why that is. Although maybe we will when we talk about light. But atoms are pulsating, all right? And it's a predictable motion, just like the pendulum, right? It's a very regular, predictable standard. We know how many times that atom vibrates, and we can learn that from the frequency of light that it gives off, essentially. Well, they started using these very, very very sophisticated clocks in a lot of their electronics when they were launching satellites into space. And they would use them to time different messaging systems, different communication relays between the satellites and each other, the satellites and Earth. Well, I don't remember when this was, let's say sometime in the 70s or 80s. They sent this, there was a satellite, just, there's hundreds of satellites, maybe thousands in space at this point in orbit around us. And it was just another communication satellite, but something went wrong. And so these satellites are supposed to orbit in these near perfect, almost near perfect circles around the Earth, right? But something happened with this satellite, and it ended up developing a really, really high eccentricity to it, right? We talked about the concept of eccentricity last time, right? It was more of an oblate, it was an elongated path. And they noticed something very funny, actually. They noticed that when that satellite came closer to Earth, that that time, that the clock, right, actually seemed to slow a bit. And when it went further away, the clock sped up, right? And they said, well, this is incredible. This is actually a proof that, that time itself has slowed down and speeds up in the gravitational wells, right, in the presence of gravity. But there's another way to look at this experiment, right, which is that when the atoms are very close to each other, say the atoms in that atomic clock, they're under a lot more pressure, right? They're being pulled on a lot harder by one another. Well, maybe that slows down their ability to vibrate, right? If I put a bunch of you and packed you into all of this whole class into an elevator, you wouldn't be able to move that much, right? So you got to be really careful with how you interpret these findings, is what I'm trying to get across to you. This concept of time fundamentally comes down to what clocks do. And if you start thinking that it means anything other than that in physics, then you wind up with some really mystical interpretations of things, which, might be fun and everything for Cosmos or something, but it's not necessarily going to lead you down any extraordinary technological paths. So, all right. Does time exist? Does time occur if there's no humans around? Well, it's a human invention, fundamentally, all right? Now, change is going to happen without humans, okay? Things are going to continue to change. But time is this standard of reference that we've set up for ourselves, okay? So that's important to consider as well. All right. Now, time on Earth would seem like something very simple to keep track of. So the length of the day, how long is the day? Well, it's something like 24 hours, right? Turns out that there's actually a couple ways of making sense of the day. The first way to make sense of the day is the one that we're all very familiar with, which is the idea of the solar day, right? This is the sun rises in the morning and it sets at night, and the next day it rises, and that's the length of the day, right? That whole cycle. Now, in some sense, there's a problem with this because actually, the Earth has moved a little bit in its position as it goes around, right? So the Earth is not only turning, but it's also moving around its path in the sun. And so it's kind of turning into it as it moves, right? And so the effect of that is that there's a little bit of extra time required. It's something like 1/365th of a day, about 4 minutes that you need to account for that's missing in the solar day, right? And so this is called the sidereal day, and this has to do with returning to the exact same point with respect to the background stars, the distant far stars. So there's actually two ways of measuring the length of the day, and they're not the same. And you can get into a little bit of a pickle if you start expecting the solar day to match up perfectly. Actually, your days will drift over time, and you can get into some trouble. So, this has been a problem, especially with timekeeping measures like this one, right? The sundial, which is a very primitive way of keeping time. Obviously, the sundial is pretty useless if you go inside. It's not very good on a cloudy day or at night either. So there's problems with that. And at any rate, the way that we've ironed out these wrinkles is by keeping track of mean solar time. In fact, mean solar time is interesting too because let's say that on Earth you were going by solar time, right? The problem is, if I travel to the east or to the west, noon, as we found out when we looked at the experiment that concerned measuring the Earth and the arc of the Earth and how the circumference of the Earth back in ancient Greece with the two cities, what you find is that when the sun is overhead at one place, it's not necessarily overhead at another place. So if we were all saying that noon is when the sun is directly overhead, which is originally what people did, the problem is that every town would have a completely different clock, right? And this is actually what people did. So if you go back, if you ever travel to Europe, you'll find that each town has a prominently displayed clock. England is a great example, this Big Ben thing. But all of the villages have these clocks very prominently displayed. And that's because they were each on their own time, right? Each town had its own time, which represented when noon was happening, right? When the sun was directly overhead. Well, that's all well and good until you get into this age of high-speed communication. I mean, can you imagine if I was trying to zoom into a meeting and it was like, the meeting's at noon, and I'm 20 minutes late because I'm meeting with somebody who's back east several hundred miles, right? It would be a disaster. And so the way they've ironed this out is essentially through this concept of time zones and mean solar time, which is essentially averaging out that solar time in a given region, which is pretty cool. And so at some point, this lack of standardization went on through the 1800s. This is actually a relatively new idea that we would standardize our time. And so they chopped up the world into these time zones, which, this is a terrible image, I'm sorry. But you get the idea that they're not exactly perfect strips, right? So different countries had to adopt which piece they wanted to go into. For instance, China's essentially decided to be part of one time zone, right? Even though it's completely, reaching into, let's say, 2 time zones over. And the effect of this is pretty hilarious because, in Tibet, which China has possessed for quite a while now, the sun's rising, it's pretty late in the morning. It's almost, 11 o'clock or noon before the sun comes up in Tibet, which is really funny. And of course, it goes down quite late as a result of that. So the time zones are pretty arbitrarily divided up. Another thing that was arbitrarily divided up is where that day changes over, right? Where do you say that where do you say that the 24 hours of those time zones start over again at? And so they drew the line right down the middle of the Pacific Ocean because they figured there's not a lot of people living there in the Pacific Ocean. And so it wouldn't bother you too much. Of course, if you live in an island right over here and you have friends in an island right next door, it might be very perplexing to you because they're going to be, a day behind you, essentially. It's actually quite funny. I have a couple of friends in Australia, and it's very, very difficult to coordinate meetings with them for me because I'm having to think about which day it is. When they say we're going to meet on Tuesday, it's not necessarily we're going to meet on Tuesday, right? It's actually probably not so. And so there's a date line that was established.
Trying to watch World Cup games this year.
Yeah, exactly. Where's the World Cup?
Well, one was in Australia.
Okay.
So the women's,
There you go.
one of them it was hard.
Yeah, exactly. Okay, I don't watch the World Cup, but that's good to know. Okay, so seasons. We talked about seasons a bit. These equinoxes are really important. We talked about the summer equinox before. The vernal equinox, right? The spring equinox came up as important when it came to establishing the right ascension 0 point. So the spring equinox is a bit easy to understand because each of the hemispheres are getting the same amount of light at that moment. Okay, because the planet is making this tilted orbit around the sun. Remember, if you learn anything in this class, the summer is not when you are closest to the sun. Please, please, please remember that. You can tell your friends. This is something we should try to correct, at least in our country. A lot of people have this misunderstanding. It's when you are tilted most towards it, actually. So you are actually closest to the sun in the winter, okay? January. All right. Now, there's a couple of other reasons for why it becomes so cold, let's say, in the winter and warm in the summer. And it has to do with the angle of those rays, right? So when you're receiving direct light, when the Earth is tilted in the northern hemisphere in the summer, when we're tilted facing those rays from the sun, what happens is that you actually get more rays per unit area illuminating the ground, right? So essentially you're getting more heat from the sun per unit area. That's a huge factor. There's also, and this is just a diagram of that, there's also the idea that as the sun is at a lower angle in the winter, it has more atmosphere to travel through. And so we're going to talk a bit about the atmosphere when it comes to climate, if we make it there, although I have a feeling we're going to have to save that conversation for next time. But the atmosphere is extraordinary in that those light rays need to be relayed through all of those atoms in order to get to you. You know, light's a really, really perplexing topic in physics because in some sense we treat it like it's just this magical ball of energy that flies from the light bulb to my eye. But I think a more realistic approach to it is that it needs to make its way from one atom to the next to my eye. And some of those atoms have the particular motion and material qualities that scatter that light in different directions, right? Actually, if I was to just, let's say if we had some fog in this room right now, you would see that effect quite easily because water interacts with light very much so. That's why cloudy days are so dark, right? And that we've had a number of them lately, at least where I live. So the necessity of that light to traverse through more atmosphere is a huge reason why it's so cold in the winter and dark as well. It's not just the angle alone. It's that interaction. All right, so another effect, I think this is a pretty useful chart. I think this is from your textbook. The effect of that, right, the effect of us being tilted more or less towards the sun in the summer or winter means that the path of the sun in the sky is higher or lower as a result of that. And it makes sense that that would be so. But it's really profound if you're up at higher latitudes, right? If you're at the North Pole or something like that. So here's a schematic which I think is quite useful. A couple of terms you might want to remember. Everybody's probably well aware of the equator or the Arctic Circle or so forth. The tropics are quite interesting, right? So at the summer, this tropic in the northern hemisphere, the Tropic of Cancer, is the midway point where the sunlight is actually illuminating it perfectly in the middle, right? And likewise, in the southern hemisphere, they have a different tropic, which, of course, is what they feel in the summer that's most illuminated. So that's where the sun is directly overhead on the northern summer solstice, that Tropic of Cancer. And this is down south, similar thing with the Tropic of Capricorn. You can see that that tropic is getting illuminated directly overhead at their equinox. All right, so let's see if this video will play. Now, if you're up far really north, you can see in the summer over here, this is a whole day, right, playing out in the summer up in Norway. It's light all of the time, right? This is pretty preposterous because this Earth is tilted that far in towards the sun up there. And of course, in the winter, it's abysmally dark all year, or all winter long. Actually, I had a friend when I was working in a lab back in San Francisco who grew up in Amsterdam, and it was just terribly depressing. She had terrible clinical depression as a result of this seasonal stuff because it's just bloody dark all winter long, right? And then you can't sleep in the summer because the sun never goes down. And then let's see if this video will play. Oh, we don't need, well, we'll get some music too. Hopefully it's not terrible. This is the North Pole at the summer. And you can see the path of the sun at the North Pole, which is pretty cool. Never, ever really sets. All right, so, and of course, you know, we're gonna be moving towards thinking about atmospheric warming and cooling now a little bit. And another interesting thing about this is that the atmosphere actually bends the light as it comes towards us, all right? And so the sun is actually not in the position that we think it's in. This turns out to be, and actually none of the stars are, which is very perplexing. So you can see a bit about how this works. Now, you might have noticed this if you guys have ever gone, I don't know, have you ever tried to catch a fish with your bare hands or something like that, or say a crawfish or something in a creek? It's actually really hard to do, right? Because you reach in and it's not where you think it's going to be, right? Because the water actually bends the light rays just a little bit. And we don't have to get into why that is necessarily right now, although maybe we'll have some time for that later. But the same thing's happening with us when we look at the sun. It's not exactly where we think it is. And so this atmosphere is a real devil when it comes to astronomy. Actually, this is why we place all of our telescopes at the top of mountains, right? Because there's less atmosphere there, which means there's going to be less of this refractive interference. And that turns out to be really, really important in terms of gauging what's going on. And the atmosphere actually also plays into this fact. So one thing that's really interesting is you might say, well, the summer solstice should be, it's the day when we're getting the most sun up here, right, in the northern hemisphere, but it's never the warmest day. Have you noticed that? It doesn't really get hot here until end of July or August, right? That's when it's absolutely miserably hot out here. And you might say, well, why is that? And again, it's because the atmosphere takes some time to take up all of that heat, right? And likewise, it's quite cold in the winter, right? So it's been cooled down. So just like heating up an ice cube or something, you have to pump that heat in. So there's a little bit of hysteresis between the most insolation, the most sun, and the warmest moment. That word, by the way, hysteresis, is really important. You can press your friends with it. It just means the lag time between an input, some impetus, and the response that you get from it. And we'll see that over and over again in terms of the effects of physical processes. When you pick at some physical process, when you give it a kick, sometimes it takes a little while for that to happen. And that lag time can teach you a bit about the physical processes that are going on. So there's a seasonal lag that's also apparent. Now, I'm going to close things down today with cracking open this idea of the sunshine and climate, and we'll finish this up next time. But the world is obsessed with carbon dioxide right now, and we'll see why that is later. So why are they obsessed with carbon dioxide? Well, because carbon dioxide is a greenhouse gas. Well, what's a greenhouse gas? Somebody help me out here. Yes?
The gases in our atmosphere that trap in warmth.
They trap the heat, exactly. So if you guys have ever, maybe some of you grew up with greenhouses in your backyard for planting. And the idea is, essentially that you can take all of that radiation from the sun and just not let the heat out once it's in there. So water vapor, right, does an enormously good job of that. That's what we were kind of pointing to in the last slide with this hysteresis, right? It does trap the heat. But there are some other different gases in addition to water vapor that make this possible. And so carbon dioxide, methane to some extent, there's a number of these greenhouse gases that trap the heat. And so the concern is that, if we produce carbon dioxide, actually we produce it by breathing, first of all, but we produce a great deal of it in our combustion engines, right? Now, the combustion engine has only been around for 100 years or so, right? And it was a real disaster for a number of other reasons before it was anything about climate change. So cities were quite disgusting by the mid-60s and 70s before they developed the catalytic converter. And actually, has anybody here traveled to Latin America, like Guatemala or something like that? Yeah. You been to Guatemala City?
Oh, no, Guatemala.
Oh, it's gnarly, right? The pollution?
Antigua, a month ago.
Okay, cool. Yeah, nice. Yeah, I was in Guatemala City a couple of years ago, and it was just difficult to breathe in that city, right? They don't have the same enforcement of this catalytic converter, right? So, and that's just a combustion product. We're not even talking about carbon necessarily. We're just talking about junk from the engine coming out. And so we've done a good job in our cities here in America of stopping that problem, right? We can actually breathe in our cities for the most part. But there's this non-toxic gas, which is carbon dioxide, which is a byproduct of combustion reactions. It's a byproduct of cellular respiration too, which is why we're all breathing it out, right? Now, it's not a bad thing by itself, right? The plants love it. Actually, it's never been greener in the history of humanity than it is today. The trees are thicker. There's more tree cover than ever before because trees breathe carbon dioxide, so they love it. Now, the fear is that if there's too much of these greenhouse gases, that they will warm the ice caps, the seas will rise, and of course, most of our cities are built by the sea. I don't know if you guys are aware of it, but most people live within a few tens of kilometers of the ocean, actually, and they always have, which is a whole, I would love to just get into that with you a little bit. So it seems like we're kind of ocean monkeys a little bit. We love to be by the water for whatever reason, and it makes a lot of sense, and there's some really cool hypotheses about human evolution concerning that. So we're afraid that the oceans are going to rise and so forth. And what I want to really, I'll pick up with this next time a little bit, but there's a lot of other things coming out of those cars, like we see in Guatemala City, that are very, very dangerous that aren't CO2. And so I'm often very concerned that when we obsess over this one molecule, we neglect to be concerned about the other problems that we have on our plate as well. For instance, does anybody have any idea what percentage of the atmosphere is carbon dioxide? Can I get some guesses? 60, 20%. What else? What if I told you that it was 0.04%, actually? Okay? So it's an inert molecule. It makes up 0.04% of our atmosphere. And there is a lot of nasty stuff coming out of our industrial manufacturing. There's increasingly less fish in the rivers every year when I go fishing. The oceans have far less fish in them. I think they're down 70% the fish they were in the 1970s. And those problems are not due to the carbon dioxide. Those problems are due to the actual industrial byproducts and so forth. And they're not getting the limelight. Last thing I want to say to you is that we have to train ourselves to pay attention to multiple factors at once. Something that the great Nazi propagandists realized back in World War II, I'm thinking of Goebbels, was that in order to really orient a big mass of people towards some end that you want them to achieve, you can only fixate on one idea. You need to just keep saying it over and over and over again, right? Whatever it is, because people can only think, it's much easier for people to hold one idea in their head at a time. And so the reason I bring that up is not because we're in danger of Nazi Germany or anything, but because we need to retrain ourselves to investigate multiple variables at once, right? We need to think a little bit bigger than this one molecule, because as we'll see next time when we start off, we're going to talk about exactly how that carbon dioxide is actually increasing and how the things that we're doing on Earth actually do seem to be contributing to changes in our climate. But there's other things going on too that don't get the press, which I think are actually more dangerous than that. And so let's pick up there next time. I think that there's a really, really intriguing story to be told. And yeah, have a great week, guys. I'll see you on Thursday.